Welcome to the last lecture for 103. You've made it. Okay, so lecture 31, 5.5, Inequalities and Systems of Inequalities in Two Variables. All right, so here's a great question. And this is often, I think, where students get a little bit of a stumble or a mix-up, so please make sure you understand this here. What is the main difference when solving an inequality versus solving an equation? So real quick, a visual here. If I was talking about an inequality, maybe an example would be x is greater than or equal to 2. An equation would be x is equal to 2. Alright, so what is one of the main differences? Well, a lot of the times the biggest one to note is the solution for an equation is a finite set. Sounds like a big word, but what do I mean? Well, for example, x equals 2. If I was to graph this, that would be the number 2. My solution right there. X equal to 2. However, if I was graphing the inequality, it's talking about x is greater than or equal to 2. So that's not only including 2, but that is including every single number greater than 2. How many numbers is that? Well, that's 3, 4, 5, on and on and on and on, and also including the numbers in between 2 and 3, then in between those numbers, and so on. There are infinitely many solutions. So the solution for an inequality is often infinite. Okay? So that is one of the biggest differences, as well as when you're working with an equation and you multiply both sides by a negative or divide by a negative. Remember, for the inequality, the sign would flip if you multiply or divide by a negative. All right, so one of the biggest things to keep in mind there. And that'll also change the way we graph our answers. So if you recall, for systems of linear equations, I'm going to go ahead and graph this on the side here. This is just going to be my scratch work. I'll erase it in a second. So for a regular linear system, we would graph our two lines, and then we would just see where they intersect at one point. But that was just a linear equation. We're not looking at equations anymore. Now we're looking at inequalities. So our solution is going to end up looking different. It's not going to be just one point, as we had for the systems of equations. So let's have a quick sort of simple visual for each of the inequality symbols. For the inequality sign less than, we might have something like, and here's where our example comes in, x is less than 3. Well, let's write this out. So translation, our solution are less than 3. Or all values less than 3. So if I was to graph this, and now remember we're working with the xy plane because we're working with a 2x2 system. So we have x and y. Let me go ahead and find 3. So we're talking about less than 3. And notice we're not including 3 in our graph. Since we're not including 3, we can't actually include that value. So remember when normally we're graphing, you use a solid bubble if we're including, or an open bubble if we're not. So if we're not actually including our boundary 3, we would use a dotted line to represent our boundary. Okay, and then our arrowhead's always important. And now we're talking about all the values that are smaller than 3, which would be all these values here. So on an exam, if you have a pencil or a pen, you could either shade with the back side of your pencil, or if you just do some nice good lines like that, that'll indicate the shading to me. Now let's take a look at less than or equal to. Let's continue with the example of 3. So x is less than or equal to 3. So once again, our solutions are less than, but this time, or equal to 3. So let's go ahead and drop in our graph again. X and y. And we have 1, 2, 3. So we're allowed to include 3 in our answer now because it can be equal to 3. So because of that, we're going to use a solid line to represent 3. So here's my solid line incoming. Awesome. And once again, our solutions are all the things that are smaller than, so I'll go ahead and shade this side because these are all the values that are smaller than 3. Now let's take a look at the other two. So greater than. Go ahead with that example of x, and this time greater than 3. So our solutions are greater than 3. Well, graphing this one, we still have the same boundary line the entire time, but notice our answer changes. So, it's not equal to. So we don't have that equal to sign underneath. So because of that, we have to use a dotted line for our boundary. We can't actually let it equal to 3. And this time our answer says x is greater. So we'll be shading the right side because these are the greater values. All right. Now we have greater than or equal to. So continue with the example, x is greater than or equal to 3 this time. So our solutions are greater than or equal to 3. So go ahead, draw in the box, draw in the graph. 1, 2, and 3. Aha! Now we can include 3 in our graph. So because we can include it, and how do I know? Well, it has that symbol there for inclusion. We'll go ahead, draw that solid line to include the 3. And again, our values are greater than 3 that are part of our solution. So we'll go ahead and shade the side that is greater than 3. Be sure to show some good shading. If the shading is not really covering the whole area, that's kind of not showing the answer. So I want to make sure you're shading the side. Alright, so those are the 4 sort of options we have with the shadings. We have the solid line, dotted line, and the shading. So here we go, the steps for solving linear inequalities in 2 variables. First off, you're going to graph the first given equation. And note, if we're working with a system, which in these ones we are, there should be the word system right there. You're going to have 2 equations. So you might have x plus y greater than or equal to some number, and then x plus y greater than or equal to some number. So these are what I'm referring to when I'm saying the first and second equation. So you're going to take the first equation and state the kind of boundary line. What do I mean by that? Well, remember, in our examples up here, we had either solid or dotted boundary lines going on over here. So you want to state that, solid or dotted. So solid or dotted. Then you're going to pick a test point. If the point makes the equation a true statement, then you're going to shade the side of the test point where that came from. Okay, this is a little abstract right now, but don't worry, we'll get there. And if the point makes the equation a false statement, shade the other side. Well, what do I mean by that? Let's take a quick look at some of these and do a test point. So let's say I was working with this equation here, x greater than or equal to 3. And I picked a test point. Let's say I picked the test point right here, the test point of negative 2. Let's plug that in. Is negative 2 greater than or equal to 3? Well, that's false, right? So because of that, we would shade the other side, because that must be the true side. However, what if I had picked a test point on the other side? And remember, this is all trying to figure out where we're supposed to be graphing. So if I had picked a test point here, for example, let's say 4, and I plugged that in, is 4 greater than or equal to 3? And you would say, yes, that's true. So because it's true, we would shade the correct side. Alright, so that's kind of what's happening with the test point. We're just figuring out which is the true side. Alright, then, so once we finish graphing the first equation, we've graphed it and we've shaded it, then we move on to the second. So some students try to graph both lines at the same time, and that usually creates some problems. So finish one thing and then move on to the next. So graph the second equation, state the kind of boundary line. Pick a test point. If it makes the equation a true statement, then you're going to shade the side the test point came from. If the point makes the equation a false statement, shade the other side. Basically, the steps for both of them are the same. And lastly, shade in the area of intersection. If they happen to overlap, because remember we're drawing two lines here. So it's possible if we drew two lines, let me make an example here. If we drew two lines, it's possible that they might intersect. And the area of intersection would be the solution to our system. Okay, so that's just an example there. All right, so if there is no area of intersection, you're going to state no solution. Always remember, if you don't get an answer, state no solution. So here we go. They're going to solve the following system of linear inequalities. Well, we're given two lines, and they're both inequalities. How do I know they're inequalities? They have the inequality symbols. Awesome. All right, so we're going to go ahead, graph them separately. I'll take the first equation. Y greater than or equal to 1/3 x minus 2. How do we graph this? Well, usually what I'll do is first I'll state the kind of line. So the kind of line is we have solid, because we have that equal to sign underneath, so I know it's going to be solid line, solid boundary, why do we state this? Well, oftentimes students will forget if they don't state it, so if you've stated it and you may graph it incorrectly, you'll still get some of the points. However, if you didn't state it and you graphed it incorrectly, you would not get those points. As usual, show as much work, or as much work as possible. Alright, so graphing this, let's go ahead and just drop the boundary sign for now, and we'll work with a regular equation because we're just graphing the boundary. Well, that's a pretty simple equation to write. We have a slope of 1/3, so a quick review on lines here, and then we have a y-intercept of 0 and -2. Now remember, we still need 3 points to graph, so we're going to have to find that other point. Let's go ahead and do a y-intercept. Sorry, an x-intercept. Intercepts are always good. So the intercept, if we had y was 0, if y is 0, let's see, so solving for the x-intercept. Actually, let me just move that to the side. So for solving for the x, or the x-intercept, we set y equal to 0. We get 1/3 x minus 2. Adding 2 to both sides, we get 2 equals 1/3 x. To get rid of that 1/3, we'll multiply both sides by 3. And we get 6 equals x. Okay, so we found the 3 important things for our system. We'll go ahead and graph. And remember, this is just the boundary line for now. We'll do the test point to figure out which side to shade. I'm going to go ahead and graph this in. Let's do green. Why not? So our y-intercept is 0, -2. X-intercept is 6, 0. And one other point, we'll go right here. -1, 3. And then we graph in our line. It's solid. Okay, so we're going to go ahead and do a nice solid line. Should be a little straighter than that, but that's okay. All right, but remember, this is an inequality. We need to figure out, am I shading this side or this side? And how do we figure that out? Well, we're going to use a test point. We'll pick one and see if it's true. Usually, I like to pick the easiest test point possible, and you might say, well, what point is that? The easiest test point possible is the origin, 0, 0. Why is it easy? Because it's zeros. However, you might get a line that crosses through it directly, and if you happen to have a line that crosses through your 0, 0 point directly, you are not allowed to use a point on your boundary line to test. Let me write that down. You cannot use a point from your boundary to test. Say that out loud in your home and people will wonder what you're talking about. Okay, so you cannot use a point from your boundary to test. It cannot be touching your boundary. It needs to be somewhere else. There is some slight lenience on that, but a good rule of thumb, do not pick from your boundary. Okay. So let me fix my other graph real quick. My little tantrum on boundary line picking. Okay, test point. What test point should we pick? I'm going to go ahead. I said pick 0, 0. I'll label it TP for my test point. Please do that on your graph to let me know which test point you picked. So for my test point, testing, we're going to test 0, 0. And what are we checking? Well, we're checking the original equation. Let's plug 0 in. So is 0 greater than or equal to 1/3 times 0 minus 2? So we'll get, is 0 greater than or equal to -2? No, it's not. Well, since this side proved to be false, we're going to shade the other side. Because if one side's false, the other side, by default, must be true. Okay, so by default, the other side must be true. So let me go ahead and shade that in. Pen was glitching a wee bit. Okay, so here we go. Nice shading. Shade all the way to the edge of the graph. Don't just sort of half-heartedly shade. Shade all the way to the edge of the graph to let me know that you know it's the entire area. If you want to clean it up a little bit, you can. You don't have to do the cleaning, but just shade to the edge of the graph, please. Okay, so we've done our testing. Okay, we're done with the first line. Huzzah! Let's go on to the second line. Just going to box off my work for the first line. So second line, we have y is less than x minus 4. Next step, what is the line? Well, since there's no equal to sign underneath our inequality, this is a dotted boundary line. Okay, so in order to graph this, let's go ahead and find the m, a slope, and then our x-intercept and y-intercept. So for graphing, we just use the regular equal sign because we were looking at the boundary. So x minus 4, let's see, what is our m? Well, m is going to equal 1 because it's the value right in the front of the x. And then our y-intercept, that's going to be the -4. But remember, we have to write it as a coordinate point, so 0, -4. And lastly, we're going to go ahead and find our third. Well, it's not technically our third point. We're going to find our x-intercept, and then we use our slope to find the third point after we graph. Okay, so let's find the x-intercept. Actually, if you want to pause the video and find it by yourself, it's a good idea. So for the x-intercept, we set y to 0. So 0 equals x minus 4. Then that means 4 equals x. Alright, so we now have all the points for our second line. And remember, it's a dotted boundary line. I'm going to go ahead and graph this in blue. So let's say we have the point 4, 0. And then we have y-intercept is 0, -4. And our slope is positive 1. So up 1 over 1, up 1 over 1, up 1 over 1. Looks like it's also at the point -1, 3. Cool, they intersect there too. But remember, that's not going to be the entire solution because we're looking at an inequality. Well, let's go ahead and graph this in. We have our 3 points. Okay. But we're not done, remember. This is inequality. We need to have a test point. Can we reuse the test point of 0, 0? The answer is yeah. We can go ahead and use that. So let's do testing. So testing 0, 0. Notice I've partitioned this so you can tell I'm working with 2 different lines here. So testing 0, 0. Let's see. So we're going to test that over here on that equation. So is 0 less than 0 minus 4? We've subbed in that for x and y. Well, is 0 less than -4? The answer is no. Make sure to state, actually, whether or not you thought it was a true statement or not. Okay, so since it's not less than 4, that means this test point is false. So we're going to shade the other side. Well, the other side is all of these lines here. Once again, just make sure to extend your sketch marks to the edge of the graph, and that's good. All right. So we have our two inequalities, but we need to shade the final intersection. So where is that area? Remember, that's going to be the very last part. This is the solution of your graph, so you need to make sure to let me know the answer. Since you can't actually write all the infinitely many numbers out, you're going to shade it. So the area that they intersect together, so just look at the crisscrossing blue and green lines. The area that they shade together is this area. Okay, so there we go, an example of a system of inequalities. Hopefully that was kind of fun to graph. I find them kind of fun. Alright, so once again, the steps are to graph each of them separately. Always make sure to figure out if you're working with a solid or dotted boundary line, and then pick a test point. Easiest one is the origin, 0, 0. If that one can't be used, then any other point will also do. So now let's take a look at solving nonlinear inequalities in two variables. Okay, so note the steps for solving nonlinear inequalities are exactly the same as the steps for solving linear inequalities. Well, that's good to know. We don't have to learn more steps, right? The only thing is you just have to remember kind of the basics on what your equations look like. So let's take a quick look at what we're given here. Pause for a second and ask yourself what kind of equations these two are. Are they linear? Are they quadratic? Would they graph a parabola, a circle, a line? What do you think? Well, the bottom one, that's definitely linear, so that's going to graph a line. I'm going to go ahead and write that down. Linear, and it's going to graph a line. The top one, however, we got the x squares and the y squares. That is going to be a circle, which will also graph a circle. Alrighty, so we have them two figured out. We have our graphing work down there. So if you want to try this by yourself and check back in with me, that would be a good idea. So for both of them, I'll go ahead and set it up. X squared plus y squared is less than 16. What kind of boundary line is this? That is going to be dotted. So dotted boundary. Go ahead and partition these off. And the next one, y less than 3x minus 2, is also going to be dotted. Once again, please note if it's dotted or not. Alright, so we're going to go ahead and graph the circle first. Well, what do we need for graphing a circle? Remember, all you need is your center and your radius. So our center, oh, well, weird, I don't see the normal form. But remember, this can just be written as x plus 0 squared, or you could do the minus 0, plus y plus 0 squared is less than, oh, actually, remember, we're just graphing the boundary, so we can use the equal sign. So my center, remember we mark it with a C, will be 0, 0. My radius will be the square root of 16. We'll take the positive square root, remember, and that'll be 4. So let's go ahead and graph that. I'll go ahead and graph that in, what color? Try to guess the color I'm going to pick. Blue. If you were right, give yourself a pat on the back. Okay, so we're going to go with blue. Center is at 0. And we're going to with a radius of 4. So right there is our radius of 4. Let's see how good of a circle I can make. Not the best. It'll do. Alright, so remember, as long as it looks like a circle, if you start having edges that are really pointy or oblong, when those things start to look pointy, that's usually where a point might get docked off, okay? So just try to curve the edges out, make sure it looks somewhat like a circle. Alright, but, oh, notice I did something wrong. Can you see what I did wrong? My boundary line, it's supposed to be dotted. Okay, so if that happened and you wrote dotted, you would still get a point because you knew it in the beginning, even though you forgot to kind of graph it. But let's go ahead and fix that on our graph. I'll take out some points, just erasing along it. You can use that with the back end of your pencil with the eraser. I find it easier to just draw the line and then erase a few pieces of it. Okay, so there we have our dotted circle. Now what do? A test point. As usual, we can pick the origin. But you might say, wait, isn't the center part of the answer? And the answer is no. The center is just the pinpoint for our radius. The normal part of our circle is just the actual outline, not the center. So we'll pick our testing. So we're going to test. Oh, I just picked red. Let's stick with red. So test the point 0, 0. So is 0 squared plus 0 squared less than 16? And the answer is no. 0 is not less than 16. So because it's not, that means the inside of the equation is not true, because that's where our test point came from. And let me label that as our test point. Okay, so the test point, that was not true, so that means we need to shade the outside. So here we go, shading the whole outside. Once again, just make sure your shading comes to the edge of the graph paper to show me that you know it's the whole area. Alright, there we go, we have shaded the circle. Sort of a bullet hole shape, I guess, maybe? Now let's go ahead and do the other line. This one should be a review, so go ahead and try graph this one by yourself. Alright, so when graphing the boundary, we're going to use an equal sign, just for the boundary. And our slope is going to be 3, and our y-intercept will be 0, negative 2. Hopefully these are just review, good review for the final coming up. So our y-intercept came from there, and our slope came from there. And then to find our x-intercept. Well, for x-intercept, we set y to 0. So if 0 equals 3x minus 2. Add 2 to both sides, we get 2 equals 3x. And finally, dividing by 3, we get 2 over 3 equals x. Okay, so we have our x-intercept, y-intercept. Let's go ahead and graph that. M is 3. What color do you think I'm going to pick? I shall pick hot pink. Bet you didn't see that coming. Alright, so we're going with hot pink. Y-intercept, 0, negative 2. That's nice and bright. And then slope of 3. We can't graph that. X-intercept, 0, 2 over 3. So about there. And we need one other point. So let's use the slope to find that other point. Our slope is 3 over 1, which means up 3 over 1. We'll go ahead and do that. Up 3 over 1 brings you to this point. Kind of clustered, so I'll go up one more. Up 3 over 1. And that point is 2, 4. Alright. Ooh, what kind of a line is this? Solid or dotted? Ah, it's dotted. Okay, let's go ahead and dot this in. And it is important because this is telling us what kind of solutions are allowed. Okay, and arrowheads. Next we need to figure out what side to shade. So we can use the same test point of 0, 0. We just keep the TP there labeled for test point. So testing, 0, 0. So plugging that in, we have is 0 less than 3 times 0 minus 2. Well, is 0 less than negative 2? The answer is no. 0 is not less than negative 2. Which means we're going to shade the side opposite to where our test point came from. And our test point came from the left side, so we're going to go ahead and shade the right. And then last thing to do is to shade their intersection. So you might say, well, why don't I just do the intersection and not all the other etch work? The etch work is part of how you show me that you found the answer, so please include all of the shading, not just the solution shading area. Okay? So that is something I will be grading for. So if you were just, or let's say on the exam you just gave the yellow shaded area, that would not receive the full credit. Please also include the other shaded areas to show me all the test work that you did. Alright, so there we go. And that is our solution. Kind of neat. Okay, so now let's go ahead and take a look at example 3. So this time we're solving a system of nonlinear equations in two variables, and both of them are nonlinear. Whew. Alright, so what are they though? Well, the first one, that's a circle. And the second one, that is, what do you think? It's a parabola. Or we'd say quadratic. It's a quadratic equation that graphs a parabola. Okay, so let's go ahead and get ready to graph these. I'll set it up as usual, x squared plus y squared less than or equal to 1. And then y greater than negative x squared plus 4. And what kind of lines do we have? Well, we have a solid line here. And we have a dotted here. Remember, we base that all on the inequality sign that we have. Okay, so for graphing the circle, well, we have a center of 0, 0, and a radius of the square root of 1, which is just 1. And that was a solid boundary line. So 0, 1. I'll go ahead and graph this one in pink this time. So center and radius of 1. Oh, that's so teensy. There we go. Now let's do a test point. Can we pick 0, 0? Yeah, we can. So let me go ahead, picking 0, 0. I'll go ahead and label it with TP. So our test point was 0, 0. And let's use it on our equation. So we're using it on x squared y squared less than or equal to 1. Plugging it in. Is that indeed less than 1? Is 0 less than or equal to 1? The answer is yes. It's true. Hey, that's the first yes we've come across, I think. Okay, so since it's true, we're going to shade the side it came from. And it came from inside the circle. Look at that little baby answer. Okay, so now we're going to go ahead and graph the next one, which is the parabola. Okay, so this is where the steps for the parabola are going to be very shortened, but this is just for graphing inequalities, all right? So if you're graphing an actual parabola by itself, keep with the 5 steps. But for an inequality, because there's so much work going on, all I want to see are the intercepts and the vertex. So for inequalities, intercepts, and the vertex. Let's go ahead and find the vertex. Alright, so for the vertex, actually let me change the color there. For the vertex, remember we use a negative b over 2a for the x value. So v sub x is going to be negative b over 2a. And our boundary line, remember we can just go ahead and think of it with the equal sign, just for our boundary. So our b value is going to be 4. And our a value is, oh, actually our b value isn't there. We don't have a b value. It's 0. Okay, so since there's no value with just the x, our b is 0. Then our a value is negative 1, so we get 0 as our x value. Then v sub y is going to be, well, we plug the 0 into our original equation, and we'll get negative 0 squared plus 4, which is 4. So v sub y is 4. Now let's go ahead and find our y-intercept. So y-intercept, we're going to set x to 0, solve for y. So we have y equals negative 0 squared. Hey, this is exactly what I just did. And it's the exact same thing. So actually, we happen to inadvertently also solve for our y-intercept. So our vertex and our y-intercept are actually the same thing. But don't worry, we don't have to worry about getting 5 points when we're working with graphing inequality parabola because there's so much work going on. Just find the vertex and y-intercept and x-intercept. Okay, so for the x-intercept, go ahead and set y to 0. So we have y to 0. We get 0 equals negative x squared plus 4. So add the x squared to both sides. And we have x squared equals 4. Square rooting both sides. We get x equals plus or minus 2. Ooh, we have 2. So we have negative 2 and positive 2, 0. Kind of squishing that up there. There we go. Let's go ahead and graph those. So our vertex is going to be at 0, 4, as well as our y-intercept. And then our x-intercepts are negative 2, 0, and 2, 0. And we'll go ahead and graph it in. Ooh, is it solid or dotted? It's dotted. Okay. So since it's dotted, we'll go ahead, dot this in. And then, last thing, we're going to have to determine which side we shade. Okay, we can still use the test point of 0, 0. So testing 0, 0 with our original equation. Always write testing. It's just a good way to let me know what you're doing and what point you're testing. So we're testing is 0 greater than negative 0 squared plus 4. And remember, what are we testing? We're testing it with the original equation. Well, 0, is that greater than 4? The answer is no, 0 is not greater than 4. So since 0 is not greater than 4, that is not true. So our answer is going to be everything outside of the equation. So let me go ahead, graph that in. Shading. Remember to shade all of your work, not just the solution point. And oh no, gosh, our shading doesn't intersect. Is that a problem? Well, it's only a problem if you're actually looking for a solution, but for us, all we can say is, well, they don't intersect anywhere. So since they don't intersect anywhere, our answer is just going to be no solution. Alright, this is another reason why you should do the side sketching work, not just the final shading area, is because sometimes they don't intersect. And this is a great example of when our two don't intersect and we don't have a solution. Okay, that is it for this section, and that is it for this course. I hope you enjoyed the lecture videos, and please email me if you have any questions about the homework or need help studying for the final.